Okay. So, alignment 2, the state of AI safety. All right, so yesterday we talked about the case for AI risk. Right, we talked about why we were allowed to anthropomorphize AIs, why they could be scary, if they were to want different things than us, that they would have the potential for a lot of destruction. We talked about why alignment might be difficult. And we talked about why this is a pressing problem. It's not off in the future. It's something we should be working on right now. Oh, yeah. And we emphasized that a lot of the risk is in sudden transitions. We're worried about these discrete changes in capabilities, discrete changes in impacting the world. So let's now take a more optimistic approach and see what we're actually doing about it. Right, so we've been working with this threat model where you're going through some training procedure, and there are these regions of lava to avoid where if you get stuck in them, maybe the damage is irreversible. Maybe you become deceptive and it's just totally opaque, and we can no longer steer back the models to become aligned. So these kinds of moments are things to watch out for, these kinds of transitions. Now, I can't claim that we currently know anything about how to detect these, but it seems like a better understanding of phase transitions in neural networks could lead to this kind of picture in the long term. Torment susceptibility. Right, if you were there for the last talk. Okay, so this talk, we're going to talk a little bit about the history. So I think it'll help understand the current landscape if we take a few steps back and understand how people thought about this and worked on this before we got to the current deep learning era. We'll talk about the alignment plan as it looks right now, how it might look with some small improvements and what the moonshot might look like. And we'll talk about specifically the role of interpretability and transparency, which is where a lot of our efforts are focused. Oops. Yeah, and so the emphasis here will be on we can try to detect and learn from these phase transitions. That might be an important component of the alignment plan. That building phase detectors slots in pretty easily into this existing alignment plan and could help with a lot of other approaches. Okay, so let's take a step back. I want you to imagine that you are 20 years, it's 20 years ago. We don't have the current deep learning paradigm yet. It's not clear whether we'll get artificial general intelligence within our lifetimes. It might be another 100 years, right? How do you go about solving or working on the question of superintelligence, working on the question of how do you address AI X risk? And this is how I see the foundations of alignment research, what I see the role of agent foundations as being, and we'll go through how this has evolved, the sort of the conventional MIRI style AI safety research, which is interesting. The question of how relevant it's going to end up being is another matter, but it's at least going to help us understand how we got here. So agent foundations. First of all, what is agent foundations, right? If you remember yesterday, we talked about the risks from power seeking. We talked about agency, optimization, goal-directedness. There's also this, another synonym would be consequentialism. These are things that are kind of scary. But at the same time, I have no idea what these terms even mean, right? Right now, these are hand-wavy concepts we throw around. We kind of know them when we see them, but we don't have a formal theory of what these things mean yet. And agent foundations starts with the observation that it sure would be nice if we had a theory of agency, if we knew what agents actually were and what they behaved like and what they did in this universe. Yeah, so they noticed, there's this observation that the existing theories of agency that we get from economics, that we get from reinforcement learning, from game theory, don't seem to suffice for understanding actual agents in the real world, or perhaps agents in the limits of lots of intelligence. Right, so we have this question of how do you study alignment when it's not clear what AGI is going to look like, what system it's going to be built on top of. Right? You do the thing all theorists do in every domain. You take some assumptions, make some approximations, take a few asymptotic limits. Right? Think of physics. We've already looked at a few examples of this. In physics, you often take a limit like the low temperature limit or the high temperature limit. These are situations where the dynamics of the system simplify, and then you can do perturbation theory. You can add, these iterative corrections to the idealized case that get better and better. Or think about approximations, and this plays very closely to asymptotics. But locally, potentials often look like harmonic oscillators, and so physicists love harmonic oscillators for this reason. Or think about making a few assumptions like the free electron gas, where you ignore interactions between electrons. And it turns out that even these simplified models can predict interesting behavior that we can actually observe in reality. So what does that look like for trying to develop a theory of agency, trying to study alignment? You make assumptions like Bayesian inference is the right model of learning. Maybe in the limit, you look at things like Solomon induction, and you assume that or you throw out the concern you might have with computability, and you just deal with systems in these kinds of limits where they have access to a hypercomputer and can compute things that we can't. You take these limits and ask the question of what does an agent behave like in the limit of lots of intelligence? How what are the stable endpoints of processes of self-improvement? You get these questions of decision theory. So decision theory, much of it studies the normative question of what's the correct decision to make in these circumstances. And the asymptotic limit, you assume maybe that as agents become smarter and smarter, they'll become better and better modeled by these normative theories. That in the limit, your theory of how an agent should act will describe how those agents actually act. Anyway, so you do the same kind of thing that you do in all other theoretical approaches when something is still being founded and it isn't totally mature. So yeah, what is an ideal agent? The sort of standard answer, the easiest answer that comes from, I guess, the economics and decision theory is agents are expected utility maximizers. So where does this come from? Well, first I want you to think of a different scenario where we have a very similar question. That question is, what is an ideal reasoner? What is an ideal thinking process that's interacting with the world and trying to update their assessment of how plausible different scenarios are, different hypotheses are? In the case of plausible reasoning, you have these Cox criteria. They're like qualitative things we would like our reasoning process to satisfy, that seem to stand on their own. Like the axioms of plausible reasoning that seem fairly reasonable, like divisibility and comparability, representing our plausibilities with the real number. Common sense and consistency. If you arrive at a conclusion through several different ways, they should all come to the same conclusion. And then conservation of information is you should use all the information available to you. So if you use these, maybe an additional Dutch book argument, you come to the conclusion that ideal reasoners do Bayesian updates. And in the decision theoretic side, we have similar kinds of arguments. So I'm thinking of the von Neumann Morgenstern axioms: completeness, transitivity, continuity, independence, and substitution. So these are saying that if you have some collections of preferences between world states, and you have them satisfy these properties, like the fact that if you prefer A to B and B to C, you should prefer A to C. Or completeness, that you have a preference, but you have some kind of preference between all things you could compare. Continuity, that you're willing to take certain bets smoothly vary between different world states. And it's a theorem that if you satisfy these axioms, you end up with your decision-making process is an expected utility maximizer. There's some utility function you can write that satisfies these properties. Yeah. Question.
What is the Dutch book argument?
So Dutch book argument, thank you for asking, is an argument of the kind that I can give you a series of bets, and you will accept every one of those bets. They're favorable for you. So you'll accept them one at a time, accept the next bet and then the next bet. And then at the end, you are guaranteed to have lost money. So you end up back at where you started, for example, but in any case, you are at a loss. So the clearest example would be with the transitivity assumption on the right, where if you prefer A to B and B to C, but NC to A, so there's a cycle there, then maybe you'd pay me a penny to move from A to B, to move from C to B, and then pay me another penny to move from B to A, and then pay me another penny to move from A to C. And you're back where you started, 2 pennies, 3 pennies, 2 pennies less. So those are the kinds of arguments that suggest that these are very natural properties that ideal reasoners should have.
It says if you have inconsistent preferences in some way, then you would lose money on these.
Yeah.
Bets. Yeah. And then similarly for the updating, it kind of says like Bayesian updating is the correct way to update. You shouldn't update it a different way.
Mm-hmm. Now, so that said, like, this is not the exclusive, you don't have to accept all of these axioms, right? So some people reject this Dutch book argument that leads to Bayesian updating, and then you end up at radical probabilism. And so you also have to update from the thing that you, like the opposites of the thing you observe. And in the decision-making case, a lot of people reject the completeness thing. They say, maybe you don't have to have preferences. You don't have to, prefer. You don't have to have preferences between all possible world states. Some of them you can just be indifferent to. And this arises when you're looking at systems of composed of subagents. I don't remember the exact details, but in any case, we know for a fact that some decision-making processes in the world, they are not well described by these things. So again, these are normative things, but even in the normative case, you can have some disagreement about what are actually the correct starting points, the correct axioms. Oops.
There's a question.
Yeah.
The indifferent or incomparable, because different just like
let's see.
Yeah,
I think it's something like if you have like A, B, C, and D, like, and the arrows are supposed to represent preferences. So you prefer B to A, D to B. Like, there's no trade you could offer me that would make me move between them, but it's not necessarily possible to end up with a utility function that assigns them equal probability, because then you would still take a trade, right? If you assign them equal probability, and and you would pay me a penny, like you would give me a penny to switch states, you would accept it. But that's not necessarily the case here. It might just be not.
There's a difference between indifference and incomparability.
Yeah.
So in one, you're indifferent between them, and then you have them. All right, I'm gonna say, so there is a difference in preferences between indifference and incomparability. Possibly these are not the right words, but I will now explain what this means. So I could be indifferent between B and C, meaning if you offer to swap, I'll be like, sure, we can swap. You could also say they're incomparable, where you won't take the swap. And basically it means like you can order them, it's sort of underdetermined, and you could order them in in a total order in two different ways.
Mhm. Yep. Okay, so yeah, the word here is coherence theorems in the case of decision making. These aren't the only ones. There are other ones like Strauss-Vage's theorem. What else do I have here? There's a complete class theorem, a Savage's theorem. Anyways, yeah. And so these are the kinds of intuitive arguments people have used to think about what would intelligence look like in the limit of lots and lots of intelligence. Yeah, so like one of these systems you end up studying is something like ICSI. Now, ICSI combines Solomon-Off induction with sequential decision theory. So what do those things mean? Solomon-Off induction is where you have some kind of you've access to a universal Turing machine, and your prior over world states weights programs by weights outputs by all programs that would produce that output according to the Kolmogorov, the prefix Kolmogorov complexity of those programs. In any case, it's a kind of canonical prior you could use to reason about sequences of numbers when you don't have access to anything else. But the problem is that prefix complexity is incomputable. We don't have access to this, so you can't do it. And then yeah, it combines that with a very traditional RL model where you're trying to maximize some reward. You're doing this expected utility maximization, and you're sending actions out into the environment. You're getting states back, and these two are separated, and you're just going through this loop again and again. So yeah, so these are the kinds of systems you think about when you're asking what does intelligence look like in the limit. Now, so what we see is a lot of the historical focus has been on this question of what do ideal agents look like, because of this intuitive argument that the more intelligent agents become, the closer they will become to these ideals. Later, we've seen more work on descriptive foundations, like what is this intermediate regime like? What are real world systems actually like? What are the next generation neural networks actually going to behave like? It might be considerably different from these ideal limits. And so I just want to highlight, I think, one particularly useful frame from Skagerbrand and Abramdensky on embedded agency. So they defied the question of embedded agency, which is, let's say the question of the first perturbative correction to the ICSI and to these ideal decision-making limits. And they note these four problem areas: decision theory, the fact that in the real world we have embedded world models. It's the case, it's not the case that I can contain a complete model of the world in my head, whereas ICSI is able to hold a complete model of the world in its head. As for robust delegation, I'm changing. ICSI isn't. ICSI is the only agent of its sort, so it doesn't have to think about how it changes in the future and how other agents like it behave. And then for the last one, subsystem alignment, ICSI is irreducible. I am divisible, and we've got enough evidence from the sort of like the dissociative personality disorder, dissociative identity disorder, plenty of other literature that suggests that we are composed of many different competing subsystems that do not all share the same goals, and some are very much at odds. Right? And in terms of decision theory, the interaction between ICSI and the world, the environment, is very well defined through this channel where actions go in, states come back. And in the real world, the boundaries are much less well defined. And so they split it up even further, do a bunch of littler problems. No. This is Adam's diagram. Yeah, I'll just leave it up so you can stare at it for a second because It's fun. Yeah, so I want to highlight, I think, two actually like genuinely interesting contributions that have come out of this line of research. Other question? No. So yeah. So two actually interesting contributions from this. So one is functional decision theory, right? So how much time do I want to spend on this? Okay, let's do a little bit. So you have Newcomb's problem. Newcomb's problem is you have two boxes in front of you. One of them is opaque and the other is transparent. The transparent one has $1,000 in it. The opaque one you can't see through. So you are told you have the option to either choose, only this opaque box or both boxes. Okay, and and the question is, which do you do? Because there's this caveat. The caveat is that there's this super intelligence outside who's called Omega, who has made a prediction of which boxes you are going to choose. And if Omega predicts that you're going to pick both boxes, then this one's empty. But if Omega predicts that you're only going to pick the opaque box, well, then it'll contain $1 million. So which do you do? And classical evidential and causal decision are so just causal decision theory makes the wrong decision. Causal decision theory tells you that you should two box. You should grab both because either this one contains $1 million or it doesn't, and so you're just increasing the amount of money that you would get by choosing both. You'll get $1 million and 1,000. Right, but that's like not even dealing with the scenario. like the premise here, the premise here is that the super intelligence has been perfect so far in its predictions. It's like, come on, do you really lack so much imagination? It's like, yeah. In any case, right? So obviously the wrong answer. And so functional decision theory says you shouldn't make the decision that leads to the best outcome, but you should select the best decision-making procedure that leads to the best outcome. And there are all kinds of other consequences. And this is worked out. I think this is like I don't know if this is actually useful for alignment, but it's interesting.
Yeah. So these may, all this talk about Newcomb's problem and these kind of paradoxes may seem like kind of besides the point, some weird kinds of nerd sniping. I didn't get it for many years, but there are various cases where you're trying to solve an actual alignment problem and these problems creep up. And one of the examples is if you might be really interested. Well, one thing in alignment we would be very interested in is a reflectively stable agent. So when you sort of unleash the AI, it might reflect and change itself in lots of ways, in a way that the original sort of alignment bounds don't really, or alignment tools don't really say much about. And then we know that you need that causal and evidential decision theorists are not reflectively stable. So you need to do this updateless decision theorist. I mean, there are actual theorems that say like if you learn in this kind of in this kind of environment, you will actually change to become such a functional decision theorist. So there are sort of toy models like that where it really does interface with something that is maybe plausibly related to AI.
I think I said this too interrogatively, but like the world we are going to end up in is going to be weird, like very, very weird, right? We are going to end up in limits that do not look like where we are right now. And yes, you want us to understand toy models like these because right now it's what we can do. And so this these kinds of situations, like they start to get at really this side of the branch, where what happens when there are copies of yourself. Right? This is a scenario that's totally conceivable with AI, where the world contains tons and tons of copies of the AI. Or what happens when there's another agent that has a world model that contains you, And it's modeled you to such accuracy that it can basically predict on many of your actions.
Predicts you very well.
Predicts you very well. It doesn't have to be perfect, but very well calibrated predictions. And these are weird kinds of situations, but they are situations we start to make sense of when we look at cases like this. And so another key problem here is the question of logical uncertainty. So, you know, we have logic, right? Which at a first pass deals with truth and falsity. At some point, you realize also uncomputability and Gödelian horrors. Yeah, so the problem is that there are statements in logic where we don't know what their truth value is yet, but they have a definitive truth value. And so you could think at first pass that you just adapt probability theory to this, but that doesn't work because probability theory, you can condition on true statements. And let's see, how does this work again? So, come up. Put you through the test.
Sorry,
Oh, wait, so if you use logical statements, you can like arbitrarily suppress. Let's
there are lots of interesting
okay.
questions.
Okay, in any case,
Okay, fine.
okay, let's get back to the real deal. So, yeah, probability theory is the best theory we have for dealing with uncertainty, but there are problems when you start adapting it to logical uncertainty. Questions about statements that we'll know the truth value of in the future, maybe, but we don't currently know the truth value of. And so a very interesting contribution in the last few years is logical induction, which has one answer to this question of how do you assign probability to these statements. And the answer they come up with is you could create a betting market of logical inductors that are trading on what they predict the resolution to be for different statements. And so the probability of a statement ends up being the trading value.
So just very shortly, logical induction, it's one of these ideal processes again of like an ideal learner in some sense, but it is better than something like IC in the sense that it is still computable, and there are lots of properties that you would want it to have that you can prove that it has. So it is computable, it converges to the truth. It doesn't get screwed over by Gödelian sentences, kind of goes around that. It has an interesting property where it trusts itself. So sort of if you in the future, it would believe, if you told it, oh, in the future, you will assign this statement high probability, then it immediately updates to assign that high probability. So it sort of believes that the future itself is trustworthy. Anyway, it is a mathematical model of a learner. And importantly, you can apply this not just to empirical statements, but to kind of tricky statements like what is the 3/10 trillionth digit of pi? Well, it's either is it 4 or is it 5? Well, is it 4 or is it not 4? Well, it's either 4 or not. So there's not empirical uncertainty, but there's logical uncertainty. I might not know at this point. But as a first guess, you might want to say it's probably 10% chance that it's 4. And logical induction sort of correctly gives all these answers. So that's kind of what it does.
Yeah. This is to summarize. I think a lot of people look at this kind of agents foundation research from the outside and think, oh, this is just one prolonged nurse, and what are these people thinking about? Yeah, I don't think that's right. First of all, these are genuinely interesting problems, and we are going to get into weird limits of this universe, and it's worth trying to understand those limits. And this is how we currently do that. Okay, so just two little highlights, right?
Conceptual question.
Yeah.
But
Yes, I've been thinking about the following way, and I'm interested if you agree. So you could think of, you talked about perturbations before, and maybe that's a useful framework. So if we start at these very ideal agents and then like perturb back to things we might encounter, well, you can get killed in one of like 10 different ways. You can get killed by the agent that's pretty lame. You can get killed by an agent that is a bit closer to being ideal. And there's like a hierarchy of problems, and maybe you need to solve all of them. Like, does this kind of consideration strike you as like mostly becomes crucial after we survive the first 3 waves and then we have more ideal things to worry about? Or is it like all these things are relevant in the first test?
Yep. This is a great question because it brings to mind something that I almost forgot to mention. I think one of the main cruxes that leads to people studying this is just how quickly do you think takeoff is? But if you expect that human level AI is extremely transient, we very quickly end up at high extremes of intelligence, then we quickly end up in these limits, right? Like the perturbations don't really matter because we spend a very short time in those perturbations. And so like, yes, there might be this overlap period. Depending on how quickly we go through this overlap period, it might be the case that the very prosaic approaches are the most important things because they just get us very deep into this. And then we've got sort of semi-aligned agents on our side that can help us solve the crazier parts of these problems. But if you think it's the case that we very quickly go through this inflection point, then yeah, you're going to want to study these weird kinds of limits very, very quickly. Yeah. So I think a lot of the model that has led in the past to thinking we get a fast takeoff, that we get FOOM, has been this thinking about recursive self-improvement. Like once you get past some threshold, like human level, you are able to design intelligences, you are able to design successors. I think what we've seen from the scaling laws, and this is where I start to get very speculative, and you shouldn't, invest too much in what I'm saying. What we've seen from the scaling laws is that intelligence seems to be very compute constrained. And maybe the more important factor than algorithmic insights and being able to edit specific nodes in your own brain is just being able to access more and more compute. And when we get to that stage, we're physically limited by how quickly you can build new GPU centers. Now, if it's the case that there's a large hardware overhang, it seems relatively likely, you can still get quick, dramatic changes. But they could look very different from what we get here because the training processes are still very long periods of time. To what? Yeah, so this question of like how quick is takeoff, right? I think it looks a little slower. Yes, because yeah, exactly. Just based on the fact that it seems to not be as much a question of manually programming intelligence, but just scaling up the compute. Now, yeah.
There's a question: is agent foundation dual use?
Alex has an answer. I don't know, but much of it is probably zero use. Yeah, maybe. I don't know. Maybe this part of it more, right? So I think, okay, so another piece of evidence towards this is that my guess is that we have a lot of abilities nowadays that some people who were studying agent foundations back in the day would have thought we're already deep into FOOM. Yeah, so we seem to be in a somewhat slower takeoff, on the order of years rather than days. And if that's the case, you want to understand this intermediate regime, the perturbative expansions, or maybe the perturbative expansions from the low intelligence case from humans. Okay. So this is when you start to get into more descriptive foundations. There was this. Oh.
Sorry, can I make a final comment on this? But yeah, I don't know. maybe I'll have to represent agent foundations a little bit. Historically, it's maybe tied with fast takeoff versus slow takeoff or these kind of things, but I think that's kind of a misleading way, or they're not really related. Agent foundations right now is just at a sort of, it's a bit about like where physics was like 400 years ago. It's just quite primitive. And there is a lot of progress in the last decades, 2 decades. It doesn't seem to go fast enough. But one could imagine that if you sort of did this, but then had 50 more years, that you really get somewhere. Now we might be dead for that. Say again? Well, yeah, I think it just really should be honest. Right now, it's just at a very ideal limit where it's just very far still from being actually applied. And it's more maybe, yeah, that's just the way it is right now. Right. Well, we hope for further breakthroughs in the future. Yeah.
Yeah. But yeah, so this is the other question. It's not just like what does the ideal limit look like, but what are agents in our world actually like descriptively? So there's this recent post from Matt McDermott that I liked a lot. He sort of tries to rephrase maybe the embedded agency model in a more descriptive way, where it's not about what the ideal limit agent looks like, but studying the actual problems that agents face in the real world. So questions like, what are the channels we use to interface with the world? What are our relationships to ourselves in the future and to other agents? Yeah, and what are our internals like? And what is also our relationship to whatever structures exist above us? And so two interesting things that I think are worth highlighting are the selection theorems, which are maybe like the descriptive superset of the coherence theorems. So this is about the question not just of like once you assign these axioms, how do you behave in accordance with those axioms? But what kind of reasoners do the selection processes that are operating on agents actually end up extracting? And those optimization processes might be STE. Yeah, how do you, exactly. So this like the selection theory stuff is bridging the gap between the descriptive case where we are now and the ideal case in the future. It's asking, how do we actually make that transition? How do selection processes actually bring us there? And I think another interesting thing, shard theory argues that a lot of this, the expected utility maximizer frame is pretty much totally garbage for describing real world systems, and that we are actually composed of a bunch of context activated I don't know what this context activated impulses in some direction, right? So we are not bags of coherent utilities, but bags of flashes of responses conditioned to specific context dependent impulses. And what you end up with is that maybe the limit of this is not something that looks like an expected utility maximizer. Maybe we need other descriptive theories. Okay, so I think like Alexander says, agent foundations deserves a defense. I think people who immediately discount it are not thinking about how crazy things could get, and so it's worth some actual thought. Yeah, it's just I think the question, like agent foundations at its heart is the question of what are agents, right? And so the normative stuff is like what we traditionally call agent foundations. This is a more charitable, larger, extended version of that. Right. So like Alexander said, unfortunately, agent foundations is not a mature theory yet. Or if it's dual use, maybe that's fortunate.
Question here.
Yes, I'm looking at Ali's question. Why wouldn't an entity composed of value shards rewrite itself into an expected utility maximizer? I mean, like, for the same reason. Yeah.
That's the argument that Miri sort of affiliated people often make.
Yeah.
That that sort of this whole chart story is irrelevant
Mhm.
because the thing will self-reflect and become this very extreme expected utility maximizer. I think a lot of the argument for Doom from Nate Soros and Eliezer Yudkowsky sort of intuitively come down to this argument.
And it doesn't even have
Whether
to be-
that's relevant or real remains to be seen.
it doesn't even have to be an explicit self-selection, but like if you imagine a system that's composed of a bunch of different subagents, and there's competition between them because there's this selection process on top of it that's pruning them and like throwing out the ones it doesn't need and giving more power, decision-making power to the ones that are most useful, you get dynamics like insubordination, like the same things that we see in collections of humans where you get a coup sometimes from some subcomponent. Just like, unfortunately, yeah, what we see with natural selection is if the selection pressure is hard enough, yeah, you get all kinds of nasty creatures and parasitic wasps and all the parasites. Things are not necessarily present. So I think it's totally possible that, yeah, you just subject these things. You wait long enough, yeah, you still end up in these weird points. But in any case, the theory of actually how that transition takes place is not fully developed, and a lot of these appeals are pretty hand-waving qualitative still. Okay, let's talk about what we would do today if we needed to align the AI. I'm going to borrow a little bit from Buck Schlegros's talk at EAG Berkeley, I think it was. Yeah, so we'll start with the current plan, what's ready to go, and talk about things that might be ready relatively soon, and then the moonshots. So currently, let's first talk about how we would go about building AGI, right? You first pre-train a very large general purpose model to predict next tokens of text and also the next tokens in whatever additional modalities you have, right? So pictures and videos, and you just train it to predict what's going to happen next. So you get this general purpose simulator that can simulate how the world is going to evolve. And then you fine tune, right? So this general purpose simulator is a bit of a scatterbrain. It's got something like multiple personality, what is it? Dissociative identity disorder is the new name. Of course, we shouldn't anthropomorphize too much, but what you want to do is to make this thing more coherent. You want it to be helpful. You don't just want that when you ask a question, it repeats a list of 5 questions that are likely to accompany that question in internet text. So you extract this butler simulacrum and you make it the dominant. You collapse the simulator onto this, right? And so we get this picture of the Shoggoth. Yeah, who knows how this fine tuning works? We first train this incomprehensible beast, and then we think that a few small modifications to it are going to make it very helpful. Oh man, this is all. I mean, like, okay. So anyway, this is the current plan to build the AGI, right? What is the current plan to align the AGI? Well, tracks pretty closely onto this. In terms of outer alignment, in terms of specifying our desires, we have techniques like RLHF, cooperative inverse reinforcement learning, constitutional AI. So what we're doing is we are teaching it from human behaviors if you're in an RL setting. So this is not as relevant for large language models. From human preferences. So we ask the AI to create a few generations, and then a human rates whichever output it prefers, and then you train it to produce that output by default next time. You just repeat this a bunch of times, or by principles. So you could actually automate this process and ask another AI to evaluate the first AI. And if you give it a handful of principles, it's better able to evaluate the AIs. And so you can automate a lot of this process. Because the thing is, the real world, the text on the internet does contain probably a decent model of what it is that humans want. Yeah, so that's outer alignment. In terms of inner alignment, making sure that these models actually desire the things we specify, we have a few approaches. So one thing is evals. We monitor the abilities that these agents have, and we look for specific precursors that would be dangerous. For example, arc evals look specifically for the ability of these models to replicate themselves. If a model can perform all the steps needed to create a copy of itself on some other, create another cloud instance of itself and replicate itself, that seems pretty central, a pretty decisive stepping point towards hostile takeover. Besides just monitoring abilities, you can actively search for harmful outputs. So now you take a red teaming approach that's practiced in software in the computer software industry, and you try to provoke it, maybe with additional AIs, maybe with teams of humans to produce harmful outputs, and then you train against those. Yeah. So the last part being adversarial training is where you actually use these things to additionally train it. These become additional parts of your objective function. So yeah, okay, so just to inject a little bit of my own opinions, I think this has a decent chance of working, at least insofar as it communicates to the AIs what we want, right? If you're pre-trained on the entire internet corpus, if you are able to do all the capabilities we want these AIs to do, you are also able to model and talk about what humans value, right? So for me, at least, most of the concern is down here. It's just like selecting AIs to produce the kinds of outputs we like. Trying to reinforce that behavior is not the same as actually making them want this terminally. And that's where most of my concern is. Okay, so that's all we got. That's how we seems fine, right? Maybe. I mean, maybe we're just lucky. Maybe this just sort of works and it's overdetermined. Could be. But I think we should try a few more things. So the things I'm most excited about that we will have access to soon are things like toy models of deception, right? So we explicitly train AIs to try to be deceptive. And as long as they're below a certain capability threshold, they can't do much damage. But we can at least study what deception looks like internally and start trying to see if our interpretability tools have any chance. We can do other things like create honeypots. So if we expect a scenario like deceptive AI, where deceptive alignment, where the AI discovers it's part of a training process, realizes that its goals differ from our goals, and then starts playing the evaluation game and like lying in wait until it's deployed, well, we can try to create scenarios that look like the AI is being deployed, or create scenarios where it looks like the AI could break out, right? Like classic psychological warfare, and trying to like all the techniques that dictators use to keep their control over their minions, right? And so that's like this is a concern, right? Like what we're getting at is like reversing the dystopia card onto the AIs. Yeah, I mean, God, it would be really bad if there's just a conservation of dystopia law in the universe where, oh man, yeah, are we the good guys? I don't know. I really don't know. But I think if we get a situation where we have a multipolar outcome and there are many different AIs, and they've all been fine-tuned differently, then maybe coordination is still pretty difficult for them. I mean, coordination is pretty difficult for us. And maybe we are able to design systems that kind of keep them in check. And if one AI tries to defect, others report it, and we can do something here. Yeah. Now, beyond this, I think the stuff that we've been talking about are what are the opportunities for interpretability, right? If you could read the thoughts of AIs, if you could detect things like it's deceptive, that would be wonderful. That would probably help quite a lot. And finally, there's this whole segment of the solution portfolio that I'm not talking about, which is governance and regulation. Like it's actually conceivable that we get regulation in place. You're not allowed to train models past a certain size, or you have to be very careful about your security procedures. There could be all kinds of other things. Again, this is not my area, but fortunately, people are working on this, and that's not the topic for this talk. All right, so this is what we'll be talking about, and in the rest of the talk, I'll make a distinction between two kinds of interpretability. There's like the full reverse engineering of neural networks. That's one limit of interpretability, and then there's the nearer case, which is developing probes, things that just give us another signal to tell us when to look for new abilities, things that correlate with a model's ability, but don't tell us exactly how the model's internal, how the model is computing its thoughts internally. Okay, what are the kinds of moonshots we could hope for? Well, maybe agent foundations works at some point, right? It just seems robustly useful to have good theories of what agents are and how they end up changing over time. Maybe we could get full reverse engineering. Now, I'm inclined to think this is not possible, but at least parts of the model we could reverse engineer. Maybe there's some kind of thing where we can replace parts. Maybe this is getting too easy, but replace parts of the model with something that's more legible to us. Do something like that. This whole umbrella of approaches that I haven't really mentioned about the question of scalable oversight. So I've talked about methods for ensuring that AIs stay aligned until human level, but how do we ensure that they stay aligned past human level when they start growing more and more capable than we are? And there's all these ideas that like all of them due to Paul Cristiano and his algorithmic complexity background, iterated distillation, amplification, humans consulting, HCH, debate, sandwiching. Anyway, most of these have like deep fundamental problems, but maybe we can come across ideas for scalable oversight that actually work. And so this is also, again, the thing I'll talk about in the next part. Okay, so let's hone in on interpretability and transparency. And I'm just going to go through a bunch of examples from the literature of what this has looked like so far, and then focus on those points that we think SLT could fit into. We'll talk about mechanistic interpretability. This question really of reverse engineering models. We'll talk about neural network probing, which is more the name that the academic literature sticks to. Mechanistic interpretability is really more of a safety, AI safety crowd subfield. And then we'll sketch a few outlines of this vision of developmental interpretability, something we'll complete towards the end of the week in the plan. So the starting point, the starting assumption for pretty much all interpretability work is this universality hypothesis. This is the idea that analogous features and circuits form across models and tasks, where features are like the fundamental unit of the neural network. Thoughts, who knows? Circuits are the ways features are connected, right? So both of these things are still confused, and like I guess especially Anthropic is working on this kind of thing, but I don't know if they know what features are. Yeah, there's this additional like linear representation hypothesis on top of this, which is the thinking that features correspond to linear directions in activation space. That's like, there are additional things on top of this. Yeah, we will talk about locality hypothesis. The question, like, could it be the case that phase transitions are localized and only involve a subset of the weights or a subset of the directions in weight space at a given moment? So yeah, there are a lot of open questions here and assumptions we're making in order to start doing the work here. Yeah, so yeah, that's the additional caveat. Like, the universality hypothesis assumes that these things can be understood. So there's some evidence for this, right? Good evidence from the vision circuits literature, where we see similar kinds of circuits form in different vision models. At the same time, this is somewhat cherry picked. So there are a bunch of neurons that are just not legible to us. Moreover, I think I just read something today about how, you know, the current state of the art vision models are becoming less legible to humans. Oh man, there are other things. This paper, birds of a feather flock together, which show that different fine tunings of BERT would lead to like systematically different completions. There was a recent paper from Bilal Chagtai, who might be there next week, who might be in the audience, where they looked at neural networks learning group operations, and they found that networks learn different representations, right? So I think we might get a talk from Bilal next week, so I'll leave it to him. So yeah, there's definitely some evidence in favor of universal hypothesis, the universality hypothesis. Also in language models where we've seen, for example, this induction head, which I think will Ronan talk about this on Thursday? Yeah. Oh, hey, Ronan. Okay. Yeah, so let's talk a little bit about mechanistic interpretability, right? Where the goal is to reverse engineer models, to understand them fully. Like, you know, the ideal here would be to write the solution for AGI inside, I don't know, your program language of choice, definitely not Python. Like, we will all die if it's Python. Anyway, and the key claim here is that models actually learn algorithms, they learn manipulations, internal manipulations that we can understand. And how we go about this is to actually, how we go about uncovering mechanistic structure, internal structure, is to actually intervene in the model's internals and see how that changes what happens to the outputs. And so this is one of the major strengths of interpretability, right? Is we have these weights on our computer, so we can do things to them. We have so much more control than any other scientific discipline in the history of science. Yeah, and it rests on this premise that hitting things with timers works. This is, again, my physicist is coming out. Yeah, so the kinds of things you can do are, you know, a lot of it falls under this heading of activation patching, where you look at, for example, the attention mechanism, and you substitute in a different value for the attention from a different pass through. You know, you can also ablate things, zero ablate things, and set them to zero. Just remove circuits. If you identify that you think these and these weights are performing this calculation, you just set them to zero, and the performance drops dramatically. Great. I think you've confirmed something along the lines of this is relevant for that. Generally, we want to be a little more careful than just zero ablating it, because there are side effects of eliminating weights. So other things you can do are mean ablating them, maybe setting the weights equal to their average, or even better, you can do things like what we saw in the beginning, replace the activations at that point from the activations in a different uncorrelated run through. And you can even use these kinds of approaches to try to rewrite knowledge. So what I'm highlighting here is this Rome paper, and you're editing the association between the Eiffel Tower so that the model thinks it's in Rome. Yeah. Other things you can do is rewrite parts of these models from scratch. And so that's what we got at with these curved neurons. People looked at a lot of matrices. You know, Chris Ola is staring at these matrices for many, many hours, and at some point, hey, I think I can write these matrices by hand. And you know, they seem to be very, very close to the real thing. Okay, let's talk about a somewhat less ambitious plan, which is neural network probing. Maybe looking for a better name than this. In any case, here the goal is to just discover features, discover, you know, parts of the model's thinking, its thoughts. Yeah, the key claim is not that there are algorithms we can understand, but it's that the representations are at least understandable. We don't have to understand fully how the model manipulates these representations and how its thought process moves, but if we understand at least like different fragments of the thought process, that can be very useful. And the method here, the main method is you build probes. So you build, you know, you train simple models, for example, or do linear regression from the activations onto things that you understand more. So you're trying to read its mind. So an example here is DeepMind's Capture the Flag paper, where they manually labeled a bunch of different game states. Like the flag is in the agent's home base, you know, the agent is in the enemy's home base, et cetera, et cetera. And they use that to classify the different activations from the model. So they sampled a bunch of activations of agents playing a game of game of Capture the Flag. And then here you see a t-SNE embedding of the activation. So they've done dimensionality reduction in a clever way that sort of preserves distances. And you see that the activations cluster in familiar ways. So like, let's see, agent flag status, you know, has this natural structure according to whether it's in the own agent's territory, in the other agent's territory. And so they seem to develop human interpretable concepts to some extent. Another example from this, remember the name? Yeah. Yeah, I mean, there's something. In any case, what they did here is something like,
The Stanford people.
It's something like the following. So on the top, you see a syntax tree for human language. This is what some linguists spend their days writing out. Right, and it's not obvious. The chef who ran to the store was out of food. It's not clear if you don't speak English that was out of food refers to the chef and not the store. So what can you do is you can right, okay, so like how would a model represent a syntax tree like this? It's not gonna be the exact same thing, but you can talk about like distances of activations, and then from those distances create a minimal spanning tree of these activations. And you find that the minimal spanning tree matches these syntax trees. Hewitt and Manning. Okay, yeah, and down below you can see that some of the attention heads seem to attend to tokens in a kind of human interpretable way, where this is looking to direct objects, and other one's looking at noun premodifiers and other things like that. Other probes, CCS, which yeah, so the picture shows what's happening. You pass a question through the model twice. Once you have it followed with the answer yes, and once you have the question followed with the answer no. And so you get these two activations, and you try to map them in a way to a probability such that the sum of those probabilities is 1. Because you expect the probability that a model assigns to the statement being true or false to sum to 1. And based off of this, you can in some cases, I mean, there's some early evidence. I think we might get a presentation on this next week from Carl. You can get more accurate predictions of what the model actually thinks than just by looking at the evidence. Something related to this, maybe it's not quite probing, but you can use GPT-4 to look at a bunch of examples of text that activate some particular neuron in GPT-4. And then GPT-4 gives an explanation, it guesses an explanation for the shared feature behind this data. Oh, it was GPT-3, okay. Yeah, then you simulate using that prompt, you try to generate new completions that would also activate this neuron. And then you score this explanation by how well those new completions fare in activating that neuron compared to the original. And so you can see, you start to get glimpses of how OpenAI imagines automating AI safety research or automating all research, everything. Yeah, here's another interesting paper from Gurney et al. So here they learn a sparse probe. So it's a probe that's only able to look at K neurons at a time. Is right. Okay. Yeah, I don't remember exactly how it works, but it only looks at a handful of activations, and it's better at uncovering features in superposition than dense probes are. And here's the Othello paper. So they learn some kind of probe on the internal activations of this model. And then you can actually invert that probe and use it to manipulate the model's beliefs. And you can do this in a way that, reliably, according to their predictions, changes the moves the AI makes. Those are the kinds of things we get at with probing. Right. So developmental interpretability, going name for the kind of vision that we're going to be looking at. And at least, one way you can think about this is, it's trying to answer the question of what happens if we hit the thing with a hammer during training to see how it reacts. What kind of information can we get from the evolution of the model and the way small collections of models move through the loss landscape. Right. We understand how neural networks learn, because understanding how they learn helps us understand how they think. And the key claim here is that the final weights might be constructed via phase transitions during the training process. And we hope to build probes that study the actual shape of the loss landscape and find traces of singularities in the loss landscape that would help us understand these phase transitions. As we saw yesterday, a lot of the risk of neural networks involves these phase transitions, so we want to understand them more. And the reality is that we observe evidence of neural networks going through phase transitions, at least in the hand wavy sense, until Friday. Then we'll see in a more complete sense. So there's the emergent capabilities literature, right? Where models seem to suddenly acquire new abilities. Now, right, there's the recently contested, there's a paper, The Mirage of Metrics, which argues that a lot of the suddenness is due to the specific metric you're plotting. If you're looking at accuracy versus some kind of loss on the benchmark, the loss could change much more continuously than this accuracy. But in any case, right, even if it is the accuracy, like the real world impact will depend on these kinds of things. And so that's also the case in physical phase transitions in nature. It is not always the case that every observable goes through a discrete change at the phase transition. Another key example is AlphaZero. AlphaZero seems to learn a lot of human-like concepts around the specific point in training. You see that on the bottom right, where it's got king safety and material, mobility, space. So this is the kind of evidence we're looking at. And this is not just across scale, but in this case, it's over the course of training. Induction heads is another excellent example that we'll see more from on Thursday. So for 2-layer transformers, you get this sudden dip in loss at a very consistent point in time. And you can reasonably understand what's going on there. And then the toy models of superposition which we will see much more of. And I'm looking forward to hearing from later. Yeah, so we want to study phase transitions because sudden capability gains are scary. These are moments that seem to be high leverage. And as we talked about in the physics talk I just gave, phase transitions are legible. Divergences are legible. And these are points in time when the macroscopic world has an easier time interacting with the microscopic world than other points. So let's detect what did you say? The torment's susceptibility. We got our jobs. Yeah. Oh, yeah. So yeah, it's duplicated. Okay. So we saw a little bit about the history of AI and maybe why agent foundations is not all crazy abstract nerd sniping. We looked at the alignment plan as it currently stands, what it might look like in the near-term future, and what the moonshots look like. And then we looked at specifically the role of interpretability in this. For mechanistic interpretability, understanding the model in full, neural network probing, understanding little parts of the model's internals, and then developmental interpretability, trying to understand the neural network from its evolution, from the way it learns. Next up, we're going to talk about mechanistic interpretability and start getting more into that toy models of superposition paper. So I'll see you tomorrow. Thank you. Yep. I can. Yep.
Yeah, so the impression I got from your talk is that the sort of developmental interpretability is sub aspect of the broader field of interpretability. I guess it makes sense, but I think we've also discussed it in sense of sort of it helping all of those other interpretability projects. Would you agree with that? How do you see those divisions?
Yeah, I think we'll probably say more about this on Friday. But the minimum viable contribution is probably something like we detect moments in which the model goes through some discrete change. You know, hopefully those don't happen too often, at least after some point in time, they don't happen too often. And then you hit pause, you run additional evals. So you look for like what has actually prompted that change or what that change has actually resulted in computationally. And then you continue training. So in that sense, detecting phase transitions is something that reduces the alignment tax. It just tells you have to run your interpretability tools and adversarial training tools less frequently. That's maybe a minimum viable contribution. And I think there's a lot more in terms of detecting, actual correlates of what's going on inside, understanding the model internals. Anybody else? If not, we can call it there.
Do you expect?
Yeah, so we saw a couple of these examples where we saw a few of these examples where it's phase transition in the hand wavy sense. There's some discrete change going on here. There are other examples. I guess grokking could be an example of this. I think it'll especially become clear when we look at the toy models of superposition. There you see the phase transitions, they're real. Oh, there's a follow-up to the question. Do you expect phase transitions to correspond to alignment changes or capability changes? Yeah, I don't know. It seems like changes in capabilities and changes in values would probably both leave traces. Yeah, yeah, exactly. Like you say, I don't know if it's easily separable. I think maybe we have tended to separate capabilities and values a little too much. And there's probably a lot of weird overlap between the two. Yeah. Oh, what do we think of Tegmark's explanation of grokking? Mostly right. So this is the explanation. Either you're referring to the representation. What is it? There's the OmniGrok paper, and then there's the towards no. Yeah, but there's one more. It came out the same year. Okay. In any case, the explanation is something like slow formation of good features. And in particular, with OmniGrok, you start in some region of weight space where the weight norm is too large. And so you have a lot of additional expressivity because if the weight norm is large, it's easier to, fit very choppy functions. The weight norm is low, you fit smoother functions. And so you have so much expressivity that you can easily memorize the data set, and then additional inductive biases. Let's call them, right? Do we have a name for the two types of phase transitions? No. Type B phase transitions, type B phase transitions, slowly push the model to the simpler thing, and they find, still a solution that achieves perfect training error, but a much lower complexity solution. Yeah, I think it's probably mostly right. I mean, like a lot of these explanations are still pretty qualitative. Yeah. Cool. All right. Is that there?
Good.
Thank you.
Pretty good.